Hi, class, and I understand some of you missed the first 20 minutes of today's lecture because of the door issue. So what I'm going to do is I'm going to just kind of recap quickly what we did in the first 20 minutes of the class. Okay. Basically, what we have done is we did a quick review of the definition of a delta function. And of course, it's 0 when t is not 0, and it's 1, sorry, when it's infinite, when t is 0. And the other definition of delta function is the integral of this delta function, okay, is 1. The integral limits at here, okay, it doesn't have to be necessarily negative infinite to positive infinite, as long as the limits include, right, this delta function, okay, and the integral will be 1 too. Okay. One of the important property that we're going to use is this even property for delta function. Okay, so we're going to make use of this guy here. The assignment number 1 and number 2 question require you to do some simplifications when you see multiplication. When you see a multiplication of function f of t and delta t. Okay. So essentially, for example, the type of question you will see is f of t multiplied by delta t, and the other type is f of t multiplied by delta t minus capital T. So this is shifted impulse function. For this particular case here, right? And how do we carry out this one here? To carry out this one here, so what we can do is, okay, so you can think of graphically, if this is your f of t, let's suppose f of t like this. Now, your delta t, right, is over here. That's your delta t, okay? So when you multiply this function with this function, essentially you multiply this graphically, so then what happens is, for anywhere, right, for anywhere over here and over here, they are all 0, right, because delta t is all 0 here. Then the value over here multiplied by 0 is 0. And the value of this one, when t is greater than 0, multiplied by this is also 0. So that means the f of t multiplied by delta t has only value, right? The value exists only at t equal to 0. So what you can do is just replace this t with 0 and multiply by delta t, right? Because delta t is only defined at t equal to 0. So that's the value of this. And don't forget to write the delta t over here, okay? Because that indicates you have a value at t equal to 0 by scale of f of 0. And for this one here, similarly, if you draw it graphically, and this is your f of t, and your delta t minus capital T is over here. Right. So the multiplication of these two functions graphically, then you can see, right, this is all 0 here, and this is 0 here. And you only will have a value exist at t equal to capital T, right? So for f of t, it really doesn't matter where the values at t that is not equal to capital T, right? So this is only matters f of capital T at where? At t here, at here, multiplied by the impulse function. Okay, so this is how you can do it. In some of the question here, for example, e to the negative 2t and delta t, right? And that'll basically be e negative 2, 0, delta t, which is delta t, right? Delta t. And if you have, let's say, delta t minus 2, right? So that'll basically e negative 2, 2, delta t minus 2, which is e negative 4 delta t minus 2. Okay. So this is how you can do some similar questions in assignment number 1, assignment number 2, problem 1. Okay. The other type of simplification that we can see that is when you see it's an integral. Okay, integral of f of t multiply by delta t, okay, or delta t minus capital T. Right, so that sort of thing. So the formality of this kind of question is, you have integral, okay, let's integrate from negative infinite to positive infinite f of t, and delta t and dt. And the other one is, right, negative infinite, positive infinite, okay, f of t, delta t minus, let's say capital T, and dt. Okay, so those are the two type of questions that you probably see in the assignment 2 problem 1. Okay. To do this one here, essentially we're gonna make use of what we just derived in the first part over here. Okay, over here. So you see, the reason I'm putting is a negative infinite, positive infinite here. Okay, we didn't know whether f of t is a cause or not, so this could be anything. So negative infinite to positive infinite, right? And just see the integrand here, right, which can be simplified to f of 0 delta t dt. Okay, and you are integrating with respect to the domain variable t, so this is a constant, so you can take this constant out of this integral, right, delta t dt. Now regarding this integral here, right, and that basically you can make use of the definition of a delta function, which give you 1, right? So you end up with just f of 0, right? And for this one here, you can do the similar thing, okay? Change the t to capital T, dt, right? That's what we did according to what we have derived over here, okay? Now, this is a constant, so take this out, like this. The integral, this one here, oh, is that still 1? Yes, it is still 1 because your impulse function is over here, but you're integrating from negative infinite to positive infinite, right? So that does include this impulse function at here. So the integral of this impulse function is still 1, and you end up with this, okay? And what you can see here is basically there's actually a special name for this one, because you see the integral of the product, right, of a function multiplied with the delta function or shifted delta function is equivalent to the function at t equal to 0 or the function at the location where the delta function is shifted to. So there's a counting here called sifting property. Okay, so it's like you are sifting the function f of t, right? What goes out, all right? What was left inside the bucket is everything that t that is not 0, and only give you the value of the t equal to 0 getting out of the bucket here, right? Sifting, right? And it's also called sampling. Okay, sampling property. Okay, yeah. Okay. So let's see, we have an example here. We integrate negative infinite to positive infinite. Okay, cosine. I think the example here. Let's see. I'll give you cosine in the class. Cosine pi t over 4 and delta t minus 2 dt. Okay. This is exactly the same format that we probably should use this one here, because your f of t here is cosine pi t over 4, and delta t minus capital T, your capital T here is 2, right? So the result here is cosine pi 2 over 4. I replace the t with 2, and this is cosine pi over 2, and which is 0, right? Which is 0. Okay. There. So that's how you can deal with this kind of question right here. Okay. Yeah. The other example that I give in the class is this. Okay. Is an example here. Okay. Is f of t and convolute delta t, and what does that equal to? Right. So in respect to however we can do that, and this is a convolution, so we might as well just write down the convolution according to the definition. Okay. F of tau delta t minus tau d tau. Okay. So for this one here, right, and this is from the definition here. How do we proceed from here, right? And the idea is to make use of this sifting property. Okay, sifting property. So if you look at this one here, I think we probably want to try this one, the sifting property over here, right, over here. But what he says here, this is f of t delta t minus capital T. Okay, so we want to use this one. We had to, change this the question into this format here. So the format here is tau, but not tau minus t. It's t minus tau. So over here, this t here, okay, is considered as a constant, okay, because we're integrating with respect to tau. So one of the property we can make use of this one here is we can make use this property so-called delta function is a even function, okay, even function. So what we can do is with this, we can change this one here, okay, we can change this one here into some sort of a use the even property here, okay. So what we do is let's take a negative sign out. So we'll see this, right? See, this basically tells you this where we can make use of even property. Because of the even function, like this delta sign here, you can let it go. Okay, you let it go. So this one equal to that. There. Now we have exactly the format that we can make use of according to the sifting property. Okay. So this we can change this tau to t. Okay, change this tau to t, and of course this f of t appear to this integral variable tau is basically become a constant, and you can take this out of this here, and delta tau minus t and d tau, right? D tau. Okay. Now the integral of this one here, right, is basically 1, and so you end up with f of t. So the integral of the convolution of f of t with delta t, you end up with f of t. Okay. In one of the assignments here, you are required to do is f of t convolute delta t minus capital T, right? So you, from the beauty of mathematics, you probably can guess this is this one here. Okay, this is this. And how would you get that? Right, you can try the procedures over here. Pretty much the same. Okay, and I can get you started. Let's see, we do the same thing. Okay, and so I'm gonna let it go to from negative infinite to positive infinite. This according to the definition of a convolution, delta. Okay, t minus capital T minus tau. Okay, yeah, t minus capital T minus tau. Okay. And what you can do is now you need to try to use this, okay, the even property, okay, and rewrite this one here into this format. Okay, rewrite this one into this format. Okay. And of course this term here, because it's the even function, so delta, right, just minus t minus capital T now, right, just like this now. And then you can proceed, okay, and you'll get exactly what you want. Okay, so I think you should be able to catch up for the rest of the unit step function, okay, based on the here. Sorry about the inconvenience, and I have talked to the security already, and they made sure that the door will be opened from now on, okay, and let's hope things will go smoothly. Okay, let me know if you have any questions. Thank you. Bye.